relentless effort to transcend Earth. The dream of extracting resources from other celestial bodies is no longer a distant science fiction scenario. Particularly, producing construction materials in situ on Mars, a planet being thoroughly studied for future settlement missions, is a revolutionary step. Australian scientists, led by Professor Akbar Randani from Spielberg University, in collaboration with the Commonwealth Scientific and Industrial Research Organization (CSIRO), have proposed a promising process to convert Mars air and red soil into iron metal, ushering in a new era for space metallurgy. The idea of self-sustaining resources on other planets is not new, but turning that idea into a scientific and engineering process is a monumental challenge. The ultimate goal of this project is to establish a sustainable space economy, where essential materials can be produced right at the point of use, instead of having to be transported from Earth. The cost of transporting materials out of Earth's gravity is extremely high, not only financially but also in terms of time and environmental impact. Every kilogram of matter launched into space carries complex costs and risks. Therefore, the ability to produce iron and oxygen directly on Mars promises to open the door to large-scale architectural projects, from robust settlement stations, refueling stations for further flights, to massive satellites assembled right in orbit or on the Martian surface. The key factor of any production process is the source of raw materials. On Mars, scientists have identified three main and abundant resources that can serve as the foundation for space metallurgy. 1. Martian air. The Martian atmosphere, though much thinner than Earth's, contains a large amount of carbon dioxide (CO2), accounting for up to 95%. This is a valuable resource not only for producing oxygen for life, but also as a source of carbon for metallurgical processes. 2. Martian soil. The Martian surface is covered by a characteristic red soil called regolith. This red color comes from the abundant presence of iron oxides, primarily iron 3 oxide Fe2O3, the oxide form of iron. This soil layer acts as Mars' natural iron ore. 3. Solar energy. Although Mars is farther from the Sun than Earth, with its fragile atmosphere, the amount of direct solar radiation reaching the surface is still to be concentrated and used as a high-intensity heat source, necessary for metallurgical reactions. The process proposed by the Australian research is a series of chemical and physical reactions, optimized to suit Martian conditions. It can be divided into three main stages: producing oxygen and carbon monoxide, generating solid carbon and thermal reduction of iron oxide. Stage 1, atmospheric extraction, producing oxygen and carbon monoxide. The core technology here is solid oxide electrolysis, a method that has been demonstrated through the MOXIE experiment on NASA's Perseverance rover. Imagine a compact machine similar to MOXIE. It extracts CO2 gas from the Martian atmosphere. This gas is then compressed and heated to an extremely high temperature of about 800 degrees Celsius. At this temperature, CO2 molecules are passed through a solid oxide electrolysis membrane, where an electric current separates oxygen atoms from the CO2 molecules. Stage 2. Recycling carbon monoxide into solid carbon. After CO is produced from the CO2 electrolysis process, the next step is to convert it into solid carbon, a necessary reducing agent for iron smelting. The proposed method is based on the disproportionation reaction of carbon monoxide, also known as the Vogt-Lord reaction. In this reaction, two CO molecules react with each other to produce one solid carbon atom and one CO2 molecule. This reaction typically occurs at specific times and may require a catalyst to increase efficiency. The solid carbon obtained is Martian coke, ready for the metallurgical process. Notably, the CO2 regenerated in this reaction can be captured and recycled back into the first stage to produce more oxygen and CO, forming a closed cycle, minimizing waste and maximizing carbon utilization efficiency. Stage 3. Metallurgy, thermal carbon reduction of iron oxide. This is the heart of the iron production process, with solid carbon already available. The next step is to combine it with Martian iron ore. Although Martian regolith is rich in iron oxide, a pre-processing step may be needed to optimize the smelting process, because this soil contains not only iron oxide but also many other minerals and elements. It is then mixed with solid carbon. This mixture is then fed into a reactor, where the temperature is raised to extremely high levels using concentrated solar energy to focus sunlight onto a single point, generating temperatures up to 1120 degrees Celsius. At these high temperatures, carbon acts as a powerful reducing agent, pulling oxygen away from iron oxides. This process is called thermal carbon reduction. The result of these reactions is the production of molten metallic iron. Research predicts that this process can achieve an iron conversion efficiency of up to 99.9%, producing a molten iron alloy containing some impurities, such as silicon, carbon, chromium, and phosphorus. According to the research team's calculation, the minimum energy required for the iron smelting reactor alone is about 3.37 megawatts per ton of molten iron alloy. When calculating the entire process, including the production of oxygen and carbon, through modules and feedstock agglomeration steps, the total energy required is about 15.51 megawatts per ton of molten iron. Although this is a significant figure, the use of abundant solar energy on Mars and the ability to recycle byproducts significantly reduce the overall energy demand from external sources. The ability to produce iron directly on Mars opens unprecedented doors for the exploration and settlement beyond Earth. Iron is one of the most fundamental and important building materials. With iron produced on site, humans can build sturdy and large-scale structures on Mars, including settlements capable of protecting astronauts from radiation in harsh environments. Reducing the amount of materials that need to be transported will make manned missions more feasible and safer. Iron can be used to repair equipment, manufacture replacement parts, or even make radiation shielding. One of the biggest barriers to deeper exploration in the solar system is the need for fuel. If structural materials like iron can be produced on site, building refueling stations on Mars becomes feasible, paving the way for further flights to the asteroid belt, or even to the outer planets. The ability to self-supply resources will be the foundation for the development of an independent space economy. Instead of just visits, Mars could become an outpost, where resources are mined and processed to serve human activities in space. Although there are still many challenges, the vision of making Mars our own is extremely appealing. The dream of building self-sustaining cities on Mars, where sturdy structures are built from the planet's own materials, is gradually becoming a reality. Every ton of iron produced on Mars will be a ton that doesn't need to be washed from Earth, saving billions of dollars and opening new limits for human capabilities. Subscribe to the Hidden_Realms channel to see the latest videos.